So we saw that 0.12% of the Sun is iron. And let's think about what that means for how much iron that really relates to. Now, the mass of the Sun is about 2 times 10 to the 30 kilograms. And if I multiply that by 0.0012 or 0.12%, then I find that the mass of the iron in the Sun is quite a considerable amount of 2.4 times 10 to the 27 kilograms of iron. Now compare that to the 6 times 10 to the 24 kilograms, which is equal to the mass of the Earth. And we can see that the amount of iron in the Sun is equal to about 400 times the mass of the Earth. So there's a lot of iron there. We believe the Sun is typical for stars in the Milky Way. So let's consider how much iron we have to create to fill the Milky Way and all the stars that have iron in our galaxy. So the mass of baryons of the Milky Way is approximately 6 times 10 to the 10 solar masses. And we know that 0.0012% of that, or a fraction of that, is iron. And so we need to have about 7.2 times 10 to the 8 solar masses of iron in the Milky Way. That is a lot of iron. And so that is iron that we have to create in the 13.8 billion years since the time of the Big Bang. Let's consider the life of a star like the Sun. It, of course, has one solar mass, and it has one solar luminosity, and it turns out its lifetime is about 10 to the 10 years. We know that from just studying the nuclear reactions in it. Now let's consider the star that's much bigger than the Sun, a big blue giant. And this object will have maybe 10 solar masses, but have a luminosity which is roughly 10 to the 4 times that of the Sun. We can figure out its lifespan because you can imagine that the lifespan of this 10 solar mass star is going to be equal to the lifespan of the Sun times the ratio of how much fuel there is in the tank. So it has 10 m solar compared to 1 m solar, so that's the ratio of the fuel, times the rate of how fast you use that fuel. And so, well, the Sun has 1 solar luminosity. These big stars have 10 to the 4 solar luminosities. And so we can expect the lifetime of one of these stars to be about 10 to the minus 3 of the lifetime of the Sun. Since the Sun has a lifespan of 10 to the 10 years, we can expect the lifetime of one of these big stars to be about 10 to the 7 years, or 10 million years. Not very long in the scheme of the universe. So we see that there are two types of supernovae. Type 2 supernovae, which produce about 0.1 solar mass of iron each, and type 1a supernovae, which produce about 0.6 solar masses of iron each. The other thing we need to know is that the ratio of SN2 to type 1a supernovae, so this will be the n of how many of these things are, is about 3 to 1. That is, for every type 1a supernova, there are about 3 type 2 supernovae. So we want to figure out what the fraction of the iron in SN2 compared to SN1a is. We know that we have 3 to 1 in terms of the number, but we have 0.1 to 0.6 in terms of how much they produce. And so when we do this multiplication out, we can see that we have 3 times 0.1 divided by 1 times 0.6. And we find that the ratio of the amount of iron formed in type 2 supernovae to type 1a supernovae is 1 to 2. If the iron production ratio of type 2 to type 1a supernovae is 1 to 2, that means that 1/3 of the Fe in the universe will be created by type 2 supernovae. Now we saw that we need about 7.2 times 10 to the 8 solar masses of Fe in the Milky Way to explain how much stuff is in the sun and all the related stars. And so the total amount formed in these type 2 supernovae would be 1/3 of that. And so we expect there to be about 2.4 times 10 to the 8 solar masses of iron formed in these type 2 supernovae. And each one of those objects has produces a tenth of a solar mass of iron each. So in total, we need about 2.4 times 10 to the 9 such supernovae in the lifetime of the Milky Way to form the iron we see. So if we look at the amount of stars in the universe, we can see if that seems sensible. So the Milky Way has in total about 4 times 10 to the 11 stars in it. Now, as we will see, the average star in the Milky Way has formed and not died. So most of the Milky Way are made up of stars that have very long lifetimes. And so of the 4 times 10 to the 11 stars in the Milky Way, 2.4 times 10 to the 9 have to supernovae. And so that's about 1 in 150 stars that are in the Milky Way today have to end up in a supernova. And so we can ask ourselves, is that reasonable? Here is a Hertzsprung-Russell diagram, or also known as an HR diagram, that shows where the stars in the universe, or at least the Milky Way, are. We can see the sun here is roughly where X marks the spot. It has 1 solar luminosity, and it's about 6,000 degrees in temperature. The stars up here, the really bright ones, are the ones that are supernovae. These are the ones that have luminosities of roughly 1,000 times the sun. And they have short lifetimes, about 10 to the 7 years, and a mass of greater than 10 solar masses. Stars like the sun turn out to be more common than those, but still not nearly as common as these stars. These are the little dwarf stars, which have lifetimes much, much longer than the life of the universe. So much longer than 1.4 times 10 to the 10 years. And so that is what make up the vast majority of the stars of the Milky Way. And so we can, when we say there are about 10 to the 11 stars in the Milky Way, that is because most of them are these stars. They've been here since day one. And the ratio, it turns out, of the number of stars of this size that are massive, that produce supernovae, to the ones that are this size down here that have very long lifetimes is about 100 to 1. And so it does seem as though these supernovae could make the iron that we see in the Milky Way.